Projectile Motion Part 2. Our first topic is relative motion. This is not Einsteinian relativity. Nowadays it's called Galilean relativity. And the idea is simply, looking at this illustration from your text by Surway, say a person is on a skateboard. They toss a ball up and down. Toss the ball straight up, it comes straight back down. Straight up, straight back down to his hand. But what if the skateboard is moving at a constant horizontal speed? Just like the projectile motion has a constant horizontal motion, a uniform motion horizontally, if air resistance is neglected. This person on their skateboard has a constant horizontal motion. So you toss a ball up, straight up, the ball will fall right back down into the person's hand. The ball will have the same horizontal motion that the skateboard and the person does. The vertical motion will be subject to gravity, regardless of whether he's moving on a skateboard or not. The ball, once it's free from his hand, is subject only to the acceleration of gravity. So the ball goes up and down, races away and races back towards the ground like any other object subject to gravity, and it has the horizontal velocity that it had right before it left his hand, the horizontal velocity that he and the skateboard have. So the ball will follow the projectile path that we've just discussed in Part 1 to an observer on the ground watching the skateboarder toss the ball. But to the skateboarder, the ball seems to only go straight up and straight down. To the skateboarder, if he's not paying attention or ignoring his horizontal motion, it seems to him the ball just simply goes up and down, straight up and straight back down into his hand. That's the heart of relative motion. Relative to him, the skateboarder, the ball is going simply up and down. Just like if we're sitting in a car, the ball will go up and down, up and down. You can toss a ball up and down with a car traveling at a constant speed, or on a boat, or on a train, or a plane. Motion on those objects. If the plane, boat, or train travels at a constant horizontal speed, then all motion on the plane seems normal. To somebody on the ground observing these, they would see the objects following projectile paths, with the horizontal motion of the train, plane, and boat included. Here's an animation showing the same thing. A cannon launches a ball from the truck bed, and it falls right back into the cannon, because the cannonball has the same horizontal motion as the constantly moving, constant speed, uniform motion of the truck. You'll see this in the experiment in ANIL also. This can help us answer the next question here on Blackboard. What you're looking at here is what's the mouse's speed relative to the factory floor. So the mouse is going to go after this cheese on the conveyor belt. So what we're looking at here is two different velocity vectors, a 3-meter and a 4-meter velocity vector. And so keeping again the horizontal and vertical, the two motions independent, we've got a motion of 4 meters or 4 speed units in one direction. Make this a little longer. And 3 in the other. It's the combination of these two independent motions like they're the components of the overall velocity. We recognize this as a 3, 4, 5 triangle. Relative to the cheese, though, the mouse is coming at it. As the cheese is moving down, it seems the floor and the mouse would be moving up. So a relative motion to different objects would be the mouse is approaching the cheese vertically or going upwards as the cheese moves down towards the mouse. So you can always flip these velocity vectors around in terms of the relative motion that's observed for the different objects. And to the mouse, relative to the mouse, it seems the cheese is approaching the mouse. Relative to the mouse's perspective. The cheese is approaching the mouse at 4 meters per second, while the cheese comes down at 3 meters per second. So let's do some more sample homework problems on projectile motion. Here's a problem about kicking a ball at an angle. Say you're punting a ball. The world's greatest punter, Andy Lee, punts a football into the air at an angle of 30 degrees from the horizontal from the field. It hits the ground 5 seconds later. So, part A, what was the greatest height reached by the ball? So what we're looking for here is we want to solve for delta y. Delta y max. Delta y being the height the object reaches. Well, we know our delta y equation for projectile motion is one of the kinematic equations. The initial in the y directions times the time plus 1/2 acceleration in the y direction times the time squared. Again, the acceleration in the y direction is g. Make sure all the variables of velocity and acceleration are all about motion in the y direction. We don't mix up the horizontal and vertical motions. We keep them independent. All right. Well, looking at what we're given here, we're given an angle. Can we use this information? We know the velocity in the y direction initially is going to be v sine theta. And that's theta is 30 degrees. So this would be v sine of 30 degrees. And what is sine of 30? Well, that's 1/2. So this is v over 2. So whatever initial velocity we have in the y direction is half the velocity overall, or just simply half the velocity. We're told it hits the ground 5 seconds later. Well, that's our overall time. But we're looking for the height that it travels on its way up. On its way up, it's only taking half the time that it does on its way back down. Let's break it up into two different independent motions. Let's say it's symmetric. Okay. So in that case, I want to substitute in the half time, not the full time. We're talking about just the motion on its way up. So I know my time. I know g. And now I'm looking for the thing that's in question is my delta y. But I don't know the initial velocity it has either. So I have two unknowns in one equation. Now I can use other kinematic equations and see if from those other kinematic equations whether I can figure out how to do it. There's many ways, once again, to do these problems when you're using kinematic equations. You can use a variety of different approaches. One trick we can do is recognize that since what we can do is recognize that since the motion on its way up is the same as the motion on its way down, draw that a little better. Let's say the initial is at the top and the final is at the bottom. This still represents half the time of flight. Since I know the motion on its way up is going to be identical to the motion on its way down, I can switch around my initial and final. Again, initial doesn't have to be the start of motion. Final doesn't have to be the end. It's wherever when I initially do my analysis and my final, or at the end of my analysis. So if I pick these as my initial and final, well, that helps a lot. Because my initial motion in the y direction is 0. It's at the very top. The initial motion it has at the very top is only horizontal. No vertical motion, otherwise it would be at the top. So if that's the case, I don't need to know what to do with this term. The initial in the y direction is now 0. And so now my delta y, what I'm looking for, can easily be solved. Because it's now 1/2 g times half the time squared. And the half the time is 2.5 seconds. So I simply plug in my numbers. 1/2 g is approximately 1/2 of 10, or 5, times 2.5 seconds squared. And that gives me the value of the height delta y. So you quickly run the numbers and submit your answer on Blackboard. So I've answered the first part of the question. Now for part B, with what speed did it leave the punter's foot? So we found how high it goes. Now I want to know is how fast was it originally kicked. What I'm looking for is the velocity. Not velocity in the x, not velocity in the y, the velocity, not its components. Well, if I just figured out from the previous part A what the height is, I can proceed from there to figure out what the overall initial velocity is. I can use the same equation I did in part A to figure out the height, plug that height back in, and then solve for the one unknown, the velocity. And through many steps I can solve it. But with these kinematic equations, we can take a different kinematic equation of the four and take a different approach and get the same answer. I always wanted to use an equation that can get you the answer the quickest, the fewest steps. So one thing we can do is we can use one of our kinematic equations is this one. The change in velocity is equal to the acceleration times time. How long you're accelerating determines your change in velocity. Again, these kinematic equations are now used for the y direction independent of the x direction. So it's acceleration in the y direction determines the change in velocity in the y direction, which is g times delta t determines the change in velocity in the y direction. Change of velocity in the y direction is v final in the y direction minus v initial in the y direction times g times delta t. Well, whether I'm talking about initial or finals going from top to bottom or bottom to top, either way, one of these, v final or v initial, is going to be 0. Doesn't really matter which one we choose. So as long as I say one of these guys is 0, going from initial on the bottom to the top as the final of 0, or the other way around. So let's say launching from the initial speed at the top, launching from initial speed at the bottom, and the top speed is 0, then I end up with the equation negative v initial in the y direction. It's negative g, because g is pointing, acceleration in the y direction is down. Then my negative signs cancel out, so I don't have to worry about that. And g is approximately 10. Again, this is half the time, because we're talking about initial, half the time up to the final spot. So 2.5 seconds divided by, 2.5 seconds. So for 2.5 seconds is my delta t of half the time. I think there was an error in the previous slide. That should be just 2.5, not 2.5 divided by 2. So 2.5 seconds times 10 gives g times half the time, half of 5. And that gives me my initial velocity in the y direction. But recall, my initial velocity in the y direction is not what I'm looking for. I'm looking for the velocity overall. And the velocity it has overall is v sine theta, because v sine theta is the initial velocity it has in the y direction. And v sine theta can be simplified because the angle, we're already told, is 30 degrees. So v times sine theta is equal to 30 degrees, and sine theta is 1/2. So again, I can simplify this. So v, the velocity it has, times 1/2 is equal to 10 times 2.5 seconds. So right there I can quickly figure out what my velocity is, 50, that the ball has at an angle of 30 degrees from the horizontal. And now on to the last part. How far horizontally did the ball travel? Well, that's just the range, or the delta x. And the delta x is equal to vx times delta t. Again, keeping that the acceleration in the x direction is 0. Vx is a constant, and v cosine theta times time is equal to the motion in the x direction. We know the time. In this case is the full time. 5 seconds is traveling both up and back down. Horizontally it's traveling the full time. We know the angle is 30 degrees. So we got the time, we got the angle, and we just solve for v in part B. So we got everything we need to solve for our one unknown and our one equation of the range delta x, how far it travels. Submit your answers for A, B, and C on Blackboard. Now you can play with this animation to practice launching a variety of different objects at different angles for target practice and help you understand what's being asked for in some of the homework problems, but mostly just for fun. Another question you have on Blackboard is this one, shoot the monkey. It's a classic question. A monkey is hanging from a tree about to let go and you want to shoot it, but of course you're going to shoot it with a medicinal banana. Do you aim above, below, or right at the monkey? Well, considering what you've learned, you know the object's going to travel, the banana is going to travel in projectile motion. The monkey lets go as soon as you shoot, he simply falls vertically. Here's animation to help you answer the question. Here's a medicinal banana about to be launched off in this animation. But if there's no gravity, what's going to happen? That's not exactly be anything interesting. Without any gravity, the banana simply just goes in a straight path, the monkey lets go, and he stays right there. Because there's no gravity, the monkey can't fall, nor can the banana fall. Wherever you aim the banana, it follows a straight path. No acceleration in the y direction, no gravity. But if there is gravity, the banana and the monkey fall. The banana falls from that straight line path. It falls with the acceleration of g. And the displacement it has as it falls is again 1/2 gt squared. The banana keeps on falling from that straight line path at a distance of 1/2 gt squared. And that's the same distance the monkey falls, because they're both subject to falling at the rate of g, thanks to gravity acting on the objects the same. Again, air resistance is negligible. And here's your proof. Okay, that's the end.